In a previous video, I derived the definitions of sine of z, cosine of z, and tangent of z in terms of exponential functions. In this video, I would like to introduce the definitions of sine of z and cosine of z in terms of its real and imaginary parts. So to define sine of z in the form where the real and imaginary parts are explicitly stated, we should start with the exponential definition of sine of z and plug in z equals x plus iy. If we do that, we end up with the expression e to the I times parentheses x plus iy minus e to the negative I times parentheses x plus iy, all divided by 2i. If we distribute the expressions for the exponents, the first term in the numerator becomes e to the ix minus y, and the second term becomes negative e to the negative ix plus y. If we use the property of exponents, we can rewrite the entire expression as e to the negative y times e to the ix minus e to the y times e to the negative ix, all divided by 2i. If we use Euler's formula to rewrite the e to the ix and e to the negative ix terms, we get this expression here. For the second term, in the numerator, e to the negative ix becomes cosine of negative x plus I times sine of negative x, because we can think of e to the negative ix as e to the I times negative x, and everything checks out when we apply Euler's formula with theta equals negative x. We can rewrite cosine of negative x plus I sine of negative x in the second term in the numerator as cosine x minus I sine of x, using the negative angle identities. If we expand the numerator, we get this expression. If we distribute the division of 2i, we get this expression. And for the second and fourth terms, the I in the numerator and the I in the denominator cancels out. So only the first and third terms still have the I in the denominator. Dividing by I is the same as multiplying by negative I, so the first term becomes negative I e to the negative y cosine x over 2, and the third term becomes I e to the y cosine of x over 2. The second and fourth terms stay the same. If we separate the expression into the real and imaginary parts, we end up with e to the y sine x over 2 plus e to the negative y sine x over 2 plus parentheses e to the y cosine of x over 2 minus e to the negative y cosine of x over 2 times I. If we factor out the sine of x for the first two terms and combine the fractions, it becomes e to the y plus e to the negative y over 2 times sine of x. If we do something similar for the imaginary part, it becomes e to the y minus e to the negative y over 2 times cosine of x. And of course, this would be multiplied by the imaginary number I. E to the y plus e to the negative y over 2 is the definition of the hyperbolic function cosh of y, and e to the y minus e to the negative y over 2 is sinh of y. So we can actually rewrite this as sine of x cosh of y plus I cosine of x sinh of y. So after doing all of this algebra, we have derived the definition of sine of z in terms of its real and imaginary components. If we want to find the definition of cosine of z where the real and imaginary parts are explicitly stated, we do the same sort of thing. We start with the exponential definition of cosine of z, then plug in x plus iy for z to get this expression. After distributing the expressions in the exponents, we get e to the ix minus y plus e to the negative ix plus y over 2. After applying the exponent rule, we get e to the negative y e to the ix plus e to the y e to the negative ix divided by 2. If we apply Euler's formula on e to the ix and e to the negative ix, then use the negative angle identities on the resulting expression, we end up with e to the negative y times cosine x plus I sine of x plus e to the y times cosine x minus I sine of x divided by 2. And if we expand the numerator, we get this expression, which is very similar to one of the expressions we had when we were deriving the definition of sine of z in terms of the real and imaginary parts. If we distribute the division and separate the expression into the real and imaginary parts, we get this expression. If we factor out the cosine of x from the first two terms, and combine the fractions, and factor out the sine of x and the negative sign from the imaginary part, and also combine the fractions, we end up with e to the y plus e to the negative y over 2 times cosine of x minus I times e to the y minus e to the negative y over 2 times sine of x. E to the y plus e to the negative y over 2 is the definition of the hyperbolic function cosh of y, and e to the y minus e to the negative y over 2 is sinh of y. So we can rewrite this as cosine x cosh of y minus I sine x sinh of y. So this is the definition of cosine of z in terms of its real and imaginary parts. So to recap, we can use the exponential definitions of sine of z and cosine of z to derive a definition in terms of its real and imaginary parts. Sine of z is equal to e to the iz minus e to the negative iz over 2I, which equals sine x cosh of y plus I cosine x sinh of y. And cosine of z equals e to the iz plus e to the negative iz over 2, which equals cosine x cosh of y minus I sine of x sinh of y.